All right, this is Public Health 4040, and we're talking about data interpretation issues. And we left off talking about systematic errors or bias that can be introduced in the study design. And we talked about selection bias, and now we're going to talk about information bias. Information bias can be introduced as a result of measurement error in assessment of both exposure and disease. So what is information bias? There's different types of it. One form of information bias is recall bias. This is where you are collecting data as an epidemiologist and you're asking questions from the participants, and there's data that has shown that individuals that are considered cases that may have a disease are better at being able to recall past events than controls. For example, one form of recall bias is that I would ask students in the class, how many of you have a direct family member with cardiovascular disease? And from that, many of you would raise your hand, and then I could ask additional questions as to what kind of components or what kind of risk behaviors do you see within your family members that may have cardiovascular disease. Another example of recall bias that I personally relate to is that my father had a heart attack, his first heart attack, 4 or 5 years ago. And prior to this, had I been asked if I had a family history of cardiovascular disease, I would have said no. But in reality, there was a lot of data to suggest, prior to even this first heart attack, that I had a family history of cardiovascular disease. So here I would have been considered a control, and I had really no recollection of some of those data collection pieces that may be associated with cardiovascular disease. Whereas now I'm very aware of what type of behaviors that my family has been associated with, and some of the genetics that might be there. Another form of information bias is interviewer bias or abstractor bias, and this occurs when the interviewers probe more thoroughly for an exposure in a case than a control. And I already used this example in class, where if I know an individual is a case, I may ask additional follow-up questions to collect more pieces of data than I would in a control where I may be more sloppy. So the question that I have is, how do you actually avoid this? And many of you should instantly think, I would hope you would think, is that you would have a double-blind type study where not only does the case and controls not know whether they're receiving treatment or not, but as an interviewer, I don't know whether or not that individual is considered a case when I'm asking those set of questions. Another form of information bias is prevarication or a lying bias, and this occurs when participants have ulterior motives for answering a question and thus may underestimate or exaggerate the exposure. And the example that I use in class is it would be like men who have sex with men. When you go out and interview certain socioeconomic status or levels of individual, as well as within different races, we know that this particular type of behavior or this type of sex does occur, but when you go and interview certain groups of men, they would deny or they would lie that they are not participating in this behavior, when in reality, when we look at disease rates and we look at how cases occur, we are able to recognize, or we're able to actually link based off of the genetics that may be associated with that infectious disease. Also, another form of lying bias would be alcohol use or prescription or illegal drug use or promiscuity surveys in conservative populations. There's been a lot of research that has shown a lying bias where you'll have, we know that there's certain rates of behavior that are occurring within specific populations based on some of the outcome data, but when you're setting up a study and you're interviewing, you have to be able to have a study design in order to be able to actually draw out those types of answers, or those appropriate answers, or those truthful answers. So another form of systematic error would be confounding, and that's where you have a distortion of the estimate of the effect of an exposure of interest because it is mixed with the effect of an extraneous factor. So for example, you have an independent variable that varies systematically within a hypothetical causal variable under the study. And I'm going to talk a lot about this over the next couple of minutes. But one way to look at confounding is, for example, is if you're looking at lung cancer and you're studying smoking, it's important to look at other risk factors that may be associated with lung cancer, because your outcome or your analysis may be distorted if you aren't taking into account some of these other exposures that can contribute to the particular outcome. Another definition is that it occurs when the crude and the adjusted measures of effect are not equal. So if there's at least a 10% difference between the crude and adjusted measure, we start to look and ask ourselves, is there a potential for a confounding that's occurring that we are not taking into account? So some of the criteria that you need to take into account when you think of can something be considered a confounding is, first of all, only confounding errors can be controlled for in the data analysis. So it's really challenging that you can't really separate out a potential confounder in your study design before you collect the data, but you need to be aware of confounders so that when you do the data analysis, you can take that into account. So what can be considered a confounder? To be a confounder, an extraneous factor must satisfy the following criteria. First of all, a confounder must be a risk factor for that particular disease. It's not necessarily a causal factor, but at least a marker for the actual cause of the disease. And that it must be associated with the exposure under study in the population from which the cases derive. So that's still kind of abstract to quite a bit of to many students, as well as it was to myself the first time I learned about confounding. So I'm going to talk a little bit more about criteria as to what could be considered a confounder. So as I said a second ago, students can relate to a confounder. First of all, must be a risk factor for the disease, as for example the lung cancer and smoking or asbestos exposure. So that could be a potential risk factor for the disease, and it must be associated with the exposure under the study in the population from which the case is derived. So the way that you could do this or look at this is that you could look at, for example, an occupational cohort study where you have the potential for breathing in or respiring in asbestos. So could potentially, if you're looking at asbestosis, would smoking be considered a confounder? And what about the age of the employee? Would the age of an employee, if you're doing an occupational cohort study and you're looking at exposures within the workplace, could potentially that age of that employee play a role or be considered a confounder? And finally, the final piece that's really important when you think about a criteria of a confounder is that it cannot be an intermediate step in the causal path between exposure and disease. Remember that a confounder has to be a causal. It actually has to cause the disease. It's not that one exposure and another exposure will ultimately only cause the disease. So the example with the occupational cohort study is that we know that smoking can cause lung cancer. We also know exposure to asbestos can also cause lung cancer. It cannot be a scenario where an individual smokes and would not develop lung cancer unless they were also exposed or they had to be exposed to asbestos, and then they would develop lung cancer. And so that's a way to look at it and say, all right, each of those exposures could act as a confounder, but they cannot be intermediate steps for one for the other. So there's an example within the textbook which I really like in order to help individuals or students be able to understand confounding, and this is Simpson's paradox. And this is a scenario where if I'm going into a store and I want to go and purchase a hat, and I'm looking at or this particular example demonstrates the association and how certain findings would be reversed when you take in or when you can actually control for confounders. And as I said, the example is I'm going to go into a store and I'm looking at black and gray hats, and I make certain assumptions based on the displays that are out there. So the first example is that when I walk into a store one day, I look on table 1, and 90% of the black hats that are there, they fit my head, whereas 85% of the gray hats would fit. Then I go over to another table, table 2, and I look at it and say, well, 15% of black hats fit. And then from that, I also see that 10% of the gray hats that are on table 2 would fit. So when you look at it initially, you would say, if I'm going to, and I didn't make any type of a purchase that day, I want to think about whether or not I'm going to buy a hat. So I said, okay, I'm going to go home, I'm going to think about it, and then tomorrow I'm going to go and make that purchase. But as I think about it and I look at the way that I collected the data, I walk into the store, and what would I instantly think? I would probably say, well, I would only try on black hats because that's the likelihood that those hats are going to fit my head. And so that's where you can take the data, for example, and say, all right, here on table 1, there's 10 hats, 9 of them fit my head, 90% of them fit. On table 1, there's 20 hats there, 17 fit, or 85%. On table 2, there was 20 black hats, 3 of them that fit, and 15%. Whereas on table 2, gray hats, there were 10 and only 1 would fit. So when I returned the next day, though, they changed up the displays, and now all the hats are found on one table. And when you take all that data from all those hats, and none of them were sold from the time I left to the time I returned, and when you combine all that data, you ultimately are able to see that 60% of the gray hats actually would fit my head versus 40%. So combining all the hats on one table is analogous, or it's an analogy to confounding. So one might quickly make the assumption that since more hats fit my head on that first day, I would likely go into the store and try and pick black hats, when in reality more or a greater percentage of the gray hats, when you combine all that data, actually fit. Another example of confounding that's more related to public health would be looking at, for example, air pollution and bronchitis. We know that are positively associated with one to another. Both are influenced by crowding, which is considered also a confounding variable. And the reason is that all too often individuals will make the assumption or will not take into account air pollution and how it potentially is related to crowding. But we also have examples of where air pollution, such as in Cache Valley, where air pollution is pretty terrible during the winter months, but it's not related to crowding. So air pollution is not an intermediate step to crowding. It's not that you have crowding and therefore you must have air pollution, terrible air quality, and therefore it will lead to bronchitis. It's important to be able to take into account these confounding variables. So is crowding a risk factor associated with the exposure under the study and not an intermediate step in the causal path? No, you have to be able to separate those out and to take those into account when you're analyzing the data or you're interpreting the data